Okay, so what do we see here? We see light passing through a slit and it's going to make it to the other side on the screen. This is the example of something called diffraction. When light goes through a tiny slit and it's going to diffract, followed by interference, right? On the screen, showing you dark fringes and also bright fringes. Now, the wavelength initially was lambda. Well, then the wavelength was bumped up to 1.5 lambda. So it became more than before. And now there's going to be a new diffraction pattern. We're supposed to now compare the new one to the old one. Now, do you know the equation that is associated with this one? Exactly. Y is equal to m lambda L over d. So what do we see in here? That y, which is the spread or the size of the interference pattern on the screen, is going to be direct with lambda.
So if this increase.
Yeah, so we're going to expect to get wider interference pattern essentially. Okay. Wide. Look for wider. The closest thing to wider is
Increase.
D. I don't know about you, but I feel like it's pretty easy. Question 2. A closed container of non-fixed volume V is filled with an ideal gas. In different trials of an experiment, the temperature of the gas is changed and the pressure inside is measured. But the volume is fixed. So PV is equal to nRT, correct? When the volume is constant, P is going to be direct with T. More T gives you more pressure. Okay. Now I think you should, last time you told me there's an equation that says PV is equal to N kB T, correct? And so we're looking to use the slope of the best fit line to find the capital N. Now, if I were to rearrange this equation, I would get P is equal to N kB over V times T. So Y is equal to, let's say, oh yeah. So you know what's happening here? The temperature I'm able to change. The question said. That means temperature is going to be my X. So mx. So my slope is these guys.
Okay.
So my slope is N kB over V. And not sure about you, but I feel like B is possible because plotting, that's the y-axis, as a function of, that's the x-axis, and this slope. It is B. What do you think?
It is.
Great. Question 3. Non-conducting rod. That means it's not a metal, right? Like maybe it's a plastic with a negative net charge is held close to but does not touch one side of a neutral conducting sphere that's initially connected to the ground. So right now we're going to be bringing that negatively charged rod close to the sphere. Your phone, my phone. Who's texting? Okay, so it's connected to the ground. So what's going to happen? We're going to have lots of positive charge in here, correct?
Yeah.
Lots of positive charge in here. And now what's going to happen? All the negatives will be sent
Down.
toward the ground. Okay. Now what do? We cut the connection to the ground. We cut the wire.
So it's gonna be positive.
Exactly correct. Okay?
Okay.
Very good. 4. A circuit consists of a battery of known EMF, a resistor of variable resistance, and a resistor of unknown resistance, connected in series. Alright, so EMF is equal to I R var plus R U. Now we're measuring the current for several known values of R var. We also create a graph to determine RU basically. Okay, so look, we are able to vary R var. So R var has to be our what? Our x-axis. So that means we have to plot our thing as a function of R var.
Yeah.
So it's not B and it's not A. Okay. So let's just talk about this equation a bit. Divide everything here by I. Just want to move the I on this side. So we're going to have EMF over I is equal R var plus RU. So Y is equal to MX plus B.
Yeah.
This is the X, the R var. And the M is 1. And the y-intercept, which physics guys call vertical intercept, is the RU.
Okay.
So it's going to be
D.
D as in dog. What do you think?
Or David.
David is a better probably. Yeah, you're right, David. Question 5. A conducting loop is positioned on the XY plane directly above a long straight wire that has a current I moving the plus X direction. Look, why don't we right now talk about the direction of the current. It's going to the right, correct?
Yeah.
Current, that means you have to use your right hand rule. So point your thumb to the right
So,
and curl your fingers. Below the wire, they're going to be into the page.
and then
Above it, it's going to be out of the page. Which of the following would induce the clockwise current in the loop? Well, look, as of now, right, the loop is experiencing a field that's going out of the page, correct? Let's talk about A. If we move the loop in the plus Y direction, that means we'll be moving it upward.
yeah.
And if we move it upward, it's going to be having or experiencing less magnetic field that's out of the page, right?
Yeah.
So it's going to experience less out of the page magnetic field. Lenz was a stubborn guy who said, nope, you can't have less of something. If you got less of it, you must have more of it. But if you have more of it, you have to have less of it. Do you get the philosophy?
Yeah.
If you have lots of money, you must donate. You don't have a lot of money, you must get donated to. Get the logic? Experiences less out of the page. That means now, Lenz says we have to experience out of the page. So must experience out of the page. Your phone is just like... Okay. So now point your thumb out of the page of the right hand and curl. What do you see? You see the current is pointing counterclockwise. What are you doing? No. You should point your thumb out of the page.
Yeah.
So put your hand on the page and point your thumb out of the page. Then you're going to curl your hand.
Okay.
Right. So that's going to be a counterclockwise motion. But this is a clockwise motion, correct? So it's not A. Let's look at B. Moving the loop in the negative Y direction. If you were to do that, you would then bring it closer to the field that's out of the page, which means experience more out of the page, but our friend Lenz says, nope, it's not allowed. You must now experience less out of the page. Okay. That means to experience less out of the page, you must experience into the page. That means now you should put the right thumb of your right hand and curl, which will give you now a clockwise current,
Yeah.
which is choice B. Good.
Yes.
Question 6. Which of the following changes to the current in the wire would induce a constant clockwise current in that loop? Look, if you were to increase I, okay? If you were to increase I, what would that do? What would that do? You would get more out of the page. How would I know? Because B is equal to mu I over 2 pi r. So B is direct with I. So more I means more field. And the field we already know is already out of the page. You get more out of the page. But Lenz says, wait a minute. If you're getting more out of the page, I'm not okay with that. We have to now get less of it.
Okay.
So now we have to get into the page. So now what I want from you, I want you to use your right hand and I want you to point that thumb into the page and curl. And it's going to be a clockwise current, wouldn't it?
Yeah.
Clockwise current.
It
It would be. It would be. So it's going to be, not C, not D. So if you increase current, you get a clockwise current. But if you want a constant, you must also go with
would.
constant, don't you?
Yes.
So 6 is choice A. A as an apple. 7 is to be left. It's fluids, we don't care about it. Do you? Good. Question 8. We got two parallel current carrying wires positioned in the X and Y axes. If it's a dot, it's out of the page. If it's an X, it's into the page. Ready?
Yeah.
So now point the thumb of your right hand to be out of the page for the top current. And you're going to be curling your fingers
So.
counterclockwise, right?
Yeah.
That's the first circle. That's the second one. Third. Fourth. Let's use red color for the one that's into the page.
So it's
Point thumb into the page, curl clockwise.
Yeah.
That's 1. That's 2. 3. So now the blue one's going to the right. Red one's going to the top. Continue. Continue. That means you now have to find the hypotenuse. But the question is the hypotenuse pulled more toward the blue one or toward the red one?
The red one.
How would you know?
According to the formula.
Which is?
Is it the mu one? So
Mu I over 2 pi r. So B is direct with I over r.
Yeah.
When the I is more and the r is less, the red is higher. That means our thing has to be more toward the red one.
Yeah. So it's B.
So it's B as in boy. Yep. Question 9. Okay. Are you familiar with the term strong nuclear force?
Yeah.
What is that?
There's like more protons.
There's what?
More protons.
Okay. I don't know what you said, but does it mean attraction or repulsion?
Of course it's fraction.
Of course, and you know it.
Yeah.
And how about electrostatic force between two protons?
They repel.
Mm-hmm. It's going to be repulsive between two protons, right?
Yes.
Okay. Now, the graphic figure 2 represents the forces. Okay. Okay, so protons 1 and 2 are separated by distance r is equal to rho in the nucleus. A force exerted. Okay. So, what do you think? Net force. What do you think about the net force at r is equal to rho? So here. Which one is higher, the Fs or the Fe? Magnitude-wise. How much is the Fe here? Let's say it's 0.7 scale unit. How much is the Fs? 1, 2, 3, right?
Yeah.
So which one is stronger?
FS.
Fs. And Fs means what? Strong nuclear force.
Yes.
The force that is basically pulling something, not pushing it away.
Okay.
Right?
Yeah.
So what's the answer going to be?
So which one is proton one?
It doesn't matter. Because they feel the same force as each other. Action, repulsion. What? Wait, what are you pointing at? Huh? D?
Yeah.
Isn't the electrostatic force larger? When R is equal to RO?
So wait, F of E is like the electrostatic force?
Yeah.
Okay.
So they're going to be pulling again, like on each other, right?
Okay.
So directed toward.
Okay.
Good? Question 10, fluids, we couldn't care less about it. 11. A sealed insulated container with a movable piston is filled with an ideal gas. The gas expands, delta V is positive. Energy does not transfer into or out by heating or cooling. That means the Q is 0. We call this an adiabatic process. Which claim is correct about the temperature of the gas? Okay. So look, delta U is Q plus W. So delta U is equal 0. And if the delta V is positive, the work is
Negative.
negative. So 0 with negative is just negative. So delta U has to be negative. Does that mean temperature increases or decreases? Decreases. So it's B as in boy.
Okay.
12. Ooh, this one. You know what's funny? Question similar to this, but in a different configuration, came back in 2013 full test. And some people say don't do the old tests. They're very wrong. Alright, small spheres 1, 2, and 3 are held in place at the corners of an equilateral triangle. Alright? Point P. Let's understand what's going on here. What do you think? So look, VO is the potential in total.
Okay.
You good?
Yeah.
I don't know about that. Question 12. Spheres 1 and 3 are held in place at their original positions. Sphere 2 then is moved far away from spheres 1 and 2. 1 and 3. Which is now F. What's the ratio? If it's moved farther away, do we care about it now?
No.
No. So, first of all, let's do initially. Okay. What was the U initially? I think we were told, right? Initially it was how much?
They didn't say.
Okay, so let's find it. Let's do spheres 1 and 3. That means K, Q1,
Q2.
Q2
Over R.
over S.
Okay. Yes.
Now let's do 1 and 2. So K, Q1, Q2.
Over S.
Let's do now 2 and 3. So K,
Q.
Q1.
Negative. Over S.
So 1 and 3. 1 and 2. 2 and 3, right?
Yeah.
This will be negative K, Q squared over S. This will be K, Q squared over S. Very good. Okay. This will be negative K, Q squared over S. If you add them all, what do you get? This is negative. This is negative. That's positive. So if you add them all three, what do you get?
Don't you like cancel the positive with the...
So you get K, Q squared negative over S, right?
Yeah.
Because positive cancels a negative, and you just have one negative left.
Okay.
That was the initial potential energy of the system. How about the final one now, with only spheres 1 and 3 being there? So now finally, we're going to say spheres 1 and 3, that means negative K, Q squared over S, right?
Yeah.
Now they want the ratio, so UF over UO, so negative K, Q squared over S over negative K, Q squared over S, which is a 1-to-1 ratio. Choice D. You like all that for a 1?
Actually, yeah.
13. Spheres 1 and 2 and 3 held in place at the original positions. Sphere 2 is then released from rest. Okay. So now 2.
Oh, it's related.
So look, 2 is going to be released from rest, right?
Yeah.
Well, look, it's getting repelled by this guy, but it's getting pulled toward this guy.
So we'll go towards the negative Q.
Well, 1 second. So if we keep drawing this, it's going to go this way. It's the resultant, we call it, which is plus X direction.
Okay. So...
And what's going to happen to the electrical potential energy of the system?
decrease.
Decrease, because it's using energy to move away.
Yeah.
So plus X and also decrease, which is choice B. 14. Spheres 1, 2, and 3 are held in place at their original positions. Sphere 4, not shown with a positive charge plus 2, is at point P. Sphere 4 is then released from rest. Okay. Look, UF minus UI is equal to K.
Okay.
That's an equation. So, to sphere 4, it's a positive charge is placed at point P. Okay. Why don't we find the okay. Why don't we find the UI, the U initial, right? So how would I do that? I would basically do I would basically multiply the voltage of the entire system by sphere 4.
Why is sphere 4?
Well, sphere 4 has a charge of 2Q, right?
Mm-hmm.
Yeah. And so let's right now it's placed at point P. So let's now find the voltage at point P by the three charges combined. What are you doing? Okay. Good. So here we were told that the voltage of the system was VO in the beginning.
Yeah.
So I'm going to say in the beginning, the charge of 2Q times VO would give me the U initially. So now the U initially is equal to 2Q VO.
Okay.
How about the U finally? The new voltage they said was VO over 3
Yeah.
times 2Q. So 2Q times VO over 3.
Okay.
And now we should do UF minus UI. Okay. And I think we should put a negative sign here because we'll get a negative number probably because we're moving away. So we're going to do 2Q VO over 3 minus 2Q VO minus sign. So it's like saying 2/3 minus 6/3. That's 4/3 QVO.
So C.
So choice C.
Piece of cake.
Sure. Question 15. In experiment, a student is asked to determine the dielectric constant of a material. Okay. And the student creates a graph that can be used to determine K. Okay. So what do we know? Capacitance is equal to kappa epsilon area over D. But D would be distance between the two plates, right? Which is here. But the area, I'll replace it with pi r squared. Because the radius is... So we're trying to... Are you good?
Yes.
Trying to find kappa, I'm not sure. Kappa epsilon pi r squared over D. Okay. You want to find kappa.
Do you...
Oh, and they have different values of r. That means what? R is the, say, x-axis.
Okay. X-axis.
X-axis, exactly. Okay, so we're gonna say C is the y axis, and r squared is the x-axis. That means the slope is equal to kappa epsilon pi over D.
Okay. So C is plotted as a function of R.
Squared.
Okay. So
Choice D.
yes.
I think we're killing it.
Yeah, easy.
16. Is that a concave mirror or a convex mirror? If you don't know that, then it's like bad.
Wait 1 second. It's concave.
Oh my goodness. It's convex, bro.
Is it?
Yeah.
Oh, concave is like the other way. Okay. Easy.
Yep. So what type of image do we get? Virtual,
Yeah, virtual.
upright, smaller than the object. And if you know your ray diagrams, which you must, the image will form here.
Yeah.
You must. That will never change. Yep.
So
it's
before
gonna be-
F.
Yeah. Okay.
Oh my god, they put before F?
Wait, where?
Oh, it says...
Oh my god. How'd you just get a nap? Okay. 17. Electron is being accelerated by a potential difference. Electron will exit the two-plate system with a speed of v, passes through a crystal. The atoms in the crystal are equally spaced. After exiting the crystal, the electrons collide with a screen A. A resulting diffraction pattern of maxima and minima is observed. Okay. So for this to happen, that means that we have diffraction occurring, and that means that electron is able to act as a waveform, right? The spacing between the maxima is YO. But now guess what? The potential difference will now be doubled up to 2 delta V. So what's going to happen to the new spacing? Okay. So, do you know your equations?
Of course.
What are they? Okay. Do you know about de Broglie wavelength? De Broglie? Lambda is equal to h over p.
Yeah.
Now, p is just mv. Okay, leave it for now. Now, k is equal to what? Half mv squared. Multiplied by m and divided by m at the same time. So mathematically, we have not changed anything. So we'll get half m squared v squared over m. So half p squared over m. So k is equal to half p squared over m. P squared is equal to m times ke. P is equal to square root of 2m times ke. Right? So now lambda is equal to h square root 2m times ke, right? Okay, so lambda is equal h over the square root of 2m ke. Now how about ke? Ke is equal to q delta v. You must know that. And so if delta v got doubled, k also gets doubled.
Okay.
So lambda is going to be inverse with 1 over the root of 2.
So this increase, this decrease.
And y is equal m lambda L over d. So that means that the lambda will decrease by a factor of 2. So the y will also decrease by a factor of 2. That means you must divide by a factor of 2. That's what decreases mean. Divide by it, which is choice B. Which of the following will correctly indicate whether the wave model of the particle model of matter best explains the diffraction pattern and provides a valid justification? Okay. Of course, diffraction requires the electron to act as a wave, not as a particle. Okay. And what follows diffraction? Interference, correct?
Mm-hmm.
Interference. So the answer is
B.
B.
Superposition.
19 not included. 20. An ideal gas is in a sealed container. The volume is constant. Leave that for a second. I don't think it matters. X to y, then y to x to z, and then z to x.
Okay.
But y to z is adiabatic. Do you know what that means, adiabatic? Q is 0. Which of the following correctly compares the temperature Tx and Ty of the gas and it states X and Y?
X and Y.
Well, which one has a higher pressure? Y. And they have the same volume. So the same volume having more pressure means more temperature. So Ty is actually 6.5 times Tx. So Ty is definitely more than Tx, definitely.
So Ty.
So it's not B, it's not A. Is the volume changing?
No.
No, it's a vertical line. So there's no work done.
So
D as in dog. Or David, as you said. 21. Which of the following best describes the motion of the piston and the average Ke of the molecules of gas from process Y to Z? From Y to Z, what's happening? Is the work positive or negative?
From Y to Z, negative.
Why?
Oh, positive.
No, it was right, but I'm asking you why. Okay, so delta V is positive, because we're expanding by 3 times. Work is negative.
Yeah.
It's adiabatic, that means Q is 0. So the sign of delta U is the same as sign of work. So delta U will be negative. That means temperature has to decrease, basically. So temperature has to decrease. And if temperature decreases, KE will also decrease with it.
Yeah.
So it's not A and it's not C.
Slowly?
Now, when they say, okay, so if Q is 0, okay, that means quickly. How would I know? Because Q with Q. But we're still, yeah, so it has to be quickly. It has to be.
So B.
Q with Q. That's a trick. If they say slowly, that means delta U is 0. It's in my first... Anyway, it's actually my exam killer cheats if you read those. Do you know what those are?
Yeah, of course.
22. From Z to X. Are we expanding or shrinking from Z to X?
Shrinking.
Okay, so delta V is negative, right?
Negative.
So work has to be?
Positive.
Okay, so it's not B and it's not A.
A.
So work is equal to negative P delta V. So negative PO.
D.
Yeah. No, wait, shoot. What are you doing? VO minus 3VO. You scared me. So 2 PO VO.
Where did the 3 go? Oh, okay.
Okay, no one asked that. 23.
That's a nice one.
Which of the following expressions is equal to the magnitude of the net electric force exerted on the sphere with a positive charge Q in the bottom right corner? Force going this way, right? And force going that way.
Yeah.
Okay, that means we gotta do what? We gotta do the Pythagorean, right? Pythagorean. So, so this guy here and this guy here. So they meet. They meet like that, right?
Yes.
Okay. So because they go at 90 degrees to each other, we're gonna have to use the Pythagorean theorem. So I'm gonna start with this guy. So the force by this guy squared, and the force by this guy squared in the square root. So K negative 2Q times Q, but there's an absolute value, it doesn't matter. So 2Q squared over.
D.
How far is negative 2Q from... Wait.
If negative 2Q from Q.
It's D, right?
D.
So just D squared.
Yeah.
Plus K. Let's not find this guy, because we're looking to find the force on the plus charge, right?
So it's Q and Q.
So that's Q squared over
D.
how far? Yeah, D squared. Okay, let's now do some simple math. So we'll get 3K Q squared over D squared under the square root. That means you must have the square root of 3, right?
So B.
Choose B.
No, that's crazy. Easy.
Wait, is there a mistake?
23.
Wait, is there a mistake? Oh shoot, I must have squared everything here.
So it's gonna be.
So yeah, that's gonna be a
4.
mistake. That would be like 5 actually.
Yeah, so C.
Root of 5. Yeah. Okay. Very good. I'm glad we fixed that together. 24. Okay, so this has to be 5. It's q squared, k squared q4 d4. And if you square root that, you get a root of 5 k q squared d squared.
So
24.
let's go this way.
Current in the resistor labeled R. So look, which one here is bigger? I2 or I1?
I1.
And which one is bigger, I1 or I3?
I1.
Okay, so basically I2 and I3 would meet up here and give you I1.
Yeah.
Okay? Which will then leave and go through this guy. That's the I1.
And to meet with I4 and then
It would meet with I4?
yeah, because I4 is going like this way.
So look, what's going to happen now is that I1 is going to separate some into this and some here. Correct?
Yeah.
Okay. And here, this guy is sending current as well. Some is going here, which is the I4, and some is going here. Okay? So look, according to Kirchhoff's law, right, the total current going into a junction, which is I1 with I4, should be equal to the current going out of the junction. So the current going to IR is I1 plus I4. So the answer is going to be choice A. Easy.
Piece
Okay.
of cake.
What's happening here?
Is that
This reminds me of the magnetic field that goes through a magnet, leaving the North Pole toward the South Pole. So the section 2 is acting as North Pole. Section 1 acts as a South Pole.
yes.
So the field is, in terms of section 1, is going the plus x direction. And in terms of section 2, also go in the plus x direction, right?
Yeah.
Because you have to connect them. So it's going to be choice D. Okay? We good so far.
Yeah.
26. You want to find then glass. Some of the light reflects, which is beam 1. Some of the light refracts, which is beam 2. You want to find NG. So which one do you use? The reflected or the refracted? Snell's law, does it care about the reflected?
No.
Never. So it's not beam 1. Cares about beam 2. Does the frequency change by changing the medium?
D.
Smart. 27, we couldn't care less about it. 28. A sealed container, right? The mass of gas X is less than the mass of gas Y. So the mass of X less than the mass of Y. But they have the same temperature. Having same temperature meaning the same KE. So KX is the same as KY.
So it's either A or C.
Yes. Now, yes, they have the same temperature, the same key, but they have different mass, different speeds, because MX is lighter, VX is more.
So C.
Yep. 28C. 29.
Little monster.
Hmm?
Little monster.
Okay. Field at P. Q1 is negative, the field's going toward it. Q2 is positive, the field's going away from it. So here we're going to be drawing it this way. So the net field will be going
This way.
like this, correct?
Yeah.
Okay. So we can break the blue one to the right into two. Into the X component and the Y component. We can also break the other blue one into two components. The X component and the Y components. So the Y components have to be added up. Correct?
Yeah.
This is 53. That's also 53. So, and you know, 1 second. And how much is this angle?
Is it 90?
90? No, probably not. Because look, this angle is the same as this angle.
Oh.
Yeah. So if this is, let's see. Let's just imagine it for a second. So if this is 37, right? What's the angle here? 53. So, same angle, right?
Yeah.
If we continue this guy here,
I think it's gonna be a 37 too.
probably, yeah. Probably. And is there a way for us to make sure?
Is there?
I think. So, both rays will have 53 as the angle. And they both have the same exact charge and the same exact dimension. So find the field by one of them, multiplied by the cosine of 53, and then double it. So we're going to say E is equal to K Q over R squared times cosine 53. Make sure your calculator is in degrees, unlike calculus, which is in radians. K Q for nano. We couldn't care less about the minus sign because of the absolute value. So 0.2 squared times cosine of 53. Let's do it.
Oh, that's crazy. Very nice.
And of course you must multiply the answer then by 2 because you have two of these things.
Very nice. 0.2. Okay, I got 900. 900 times the 2. That's 180. 800. Did you get the same thing?
One second. I got 1083.
83?
1083.
I got 1800.
I mean, how far? That's not right. Wait, how'd you do that?
I did.
If you don't put the cosine, you get C. We must put the cosine. $30. Isn't resistance equal to resistivity, length over the area?
Yeah.
So isn't resistance equal to, if we put length apart, resistivity over the area?
Yes.
So y is equal to x times m. So the slope is resistivity over the area. Let's find the slope. This will be 2.5 with 0.20. This will be 0 and 0. So resistivity over the area, which is pi r squared. So divide diameter by 2 and square it, is equal to the slope, which is 0.20 over 2.5. Let's find resistivity. So that means you just have to do pi 2.5 times 10 to the power of negative 4 squared times 0.2 over 2.5. And you will get 1.57, which is B. 31 is to be skipped, it's just fluids. 32 is not skipped. So, the object is within the focal length in the case of a convex lens or a converging lens. That means the image has to be upright.
It's
Actually upright and enlarged. It's the sixth case of a converging lens. Okay, has to be upright
So
and enlarged.
BB.
B, what are you talking about? Check it out, it's the sixth case. I have put all the cases in the Khalid sheets. Okay. 33. A container is full of an ideal gas. The following can be varied. You want to get a graph, right?
Yes.
A best fit line. So, best fit line, right, basically means something like this. That means you're looking for a direct relationship, right? PV is equal to nRT. So if you plot P versus T, you get direct. But if you plot P versus 1 over T, you get inverse, right?
Yeah.
P and V are right next to each other. They're stuck. That means they're going to be inverse with each other. So if you plot P versus 1 over V, you get a straight line going down. Going up.
Yeah.
But if you plot P versus V, you get an inverse relationship. Okay?
So is it V as a function of n?
Yeah, V with N. So plot V here, plot N here, straight line going up. 34. I have a hard time reading this one, like the figure is a bit messed up, but I think that the arrows are going out, right? For both of them. If the arrows are going out, it has to be electric field, not gravitational field. So it has to be electric. So it's not C and it's not D.
Which are sphere 1 has Q1?
Yeah, of course. Okay, what I see is that the fields are pushing to the left, right?
Yeah.
By sphere 2. That means they're more. That means the Q of sphere 2 is more powerful.
Yes. So B.
So I'm gonna go with B. Yeah, that's what I feel. What do you feel?
Same thing.
Okay. Of course, from 1 to 2, you're going to have an increase in the voltage, right? Because you're going through a battery, right? So, and you cannot have disconnected, so it's not D and it's not C. So how are these two different?
Wait a second. Is it B?
Why?
Okay, so basically, from 1 to 2, it's increasing.
Yeah.
And then it's at rest constant. Until it reaches the 3, which is the resistance, it will decrease.
It has to drop.
Yeah, and then from 4 to 5, it's constant.
Yeah.
And then it decreases when it
Yeah.
passes through the 2R resistance.
Okay.
So it's B.
That's why, because here the droppage is for a single R, but here the droppage is twice as steep because it's 2R, correct?
Yeah.
So it's B. Exactly.
Logic works.
36. Okay, so proton inside a magnetic field, right? So Fm is equal to QVB for the proton. For the alpha, Fm is equal to QVB. So do they have the same charge? No, alpha has twice the charge, right?
Yes.
That's 2QVB. Yeah. So alpha with this velocity, they have the same velocity, right? Alpha and the proton move with the same velocity. They both have V. So which one is experiencing more force?
Alpha?
Alpha by how many times more?
2.
2 times more. So it's B. Good?
Yeah.
37.
Okay.
Let's use the mirror's equation. So 1 over F, 1 over SO, plus 1 over SI. Is the mirror here concave or convex?
Concave.
Concave. That means the F has to be positive. 1 over 5, 1 over 30, plus 1 over SI. So now do your magic with the calculator. Now let me know how much you get.
Got 1 over 6.
Flip it, please. Okay, so 6, right?
6. Yeah.
It's not B, it's not A. Okay, now
Let's find M.
the object, right, is so far from F.
Yes.
As long as the object is okay, so look, if the object is here at 10, it would be the same size, object and image, same size.
Yes.
But when it's farther away, magnification has to be less than 1.
Okay.
Okay, when it's at C, which is double the F, same size. But if it's more than C, it's less than 1. Sorry?
So it's far. Okay.
So it has to be, this one.
C.
Yeah.
Easy.
38. Okay, energy and wavelength are going to be inverse with each other, correct?
Yeah.
So less wavelength means more energy. So lambda 2 is less than lambda 1. So E2 is more than E1. E2 is what? More than E1.
Yeah.
So it's not A. It's just C, right?
Yes.
What do you think?
Yeah.
Photon 3. How about photon 3? Oh, sorry. It is either C or D because E2 is more than E1, but we're not sure about E3, right?
Yeah.
We actually have to do some math here. So we can, convert that energy into wavelength and compare.
Can we multiply?
I wish you were right. So E is equal to Hc over lambda. Hc is 1240 eV lambda. Lambda is equal 1240 over 0.6. How much will that be?
So 1 to 40, 0.6. That's like 2066.
What? 2000 what? How much? 2000?
2066.66.
Okay.
Yeah.
So it has the longest wavelength, it has the least energy, right?
Yeah. So yeah, C.
So C. Photons 1 and 2 are incident on metal with a work function. Okay, we should actually use the wavelength to find the to find their energy. E is equal to Hc over lambda. Do it for both. Hc over lambda. So because your wavelength is nanometer, 1240 over 620. 1240 over 155. Let me know how much you get
The
here.
first one is 2.
Okay.
And then for the second one, it's 155. It's 8.
So which one can overcome the work function of 6? Only photon 2, correct?
Yeah.
Okay. That was going to be choice B. Question 40. We should bring up this equation. Q over T, it's in your equation sheet, is equal to K, resistivity, L, delta temperature. I think, was it L on top or was it area on top? It was area on top. Yeah. Over L. So Q over T is going to be the slope here, right?
Yeah.
What's our slope? 30, 600 with 0, 0. So it's going to be 600 minus 0 over 30 minus 0, which is 20. Our slope is equal to 20. Now, K is the resistivity or the thermal conductivity constant, I mean, which is K. A is the area, which is area of
Cylinder.
the cross section, yani pi r, pi r squared.
So pi r squared.
Delta T is the change in temperature, which is 60, and L is the length, which is 0.80. So how would you find the K now?
Do you rearrange?
Pi 0.25. Okay.
Times 60. Over 0.80 times 20. I got 1.35.
So 1.4, right?
Yeah.
Okay. Question 41. This positive rod will cause the negative charges from both spheres to be here, right? This one will be
Positive.
positive. But what's happening is we're connected to the ground, and the ground has lots of electrons, lots of free electrons. So it will also move up here to make this into a like neutral. So 1, 2, 3, 4, 5. So now sphere S is neutral, but R is
Negative.
negative. Now with the rod close by, this will remain negative.
This will be neutral.
This will be neutral. 1, 2, 3, 4, 5. So S is going to be neutral, R is going to be negative, which is choice D. Okay. So question 42. A student must experimentally determine the resistivity of a cylindrical resistor of unknown. Okay, so look, the equation is R is equal resistivity length over the area. So resistivity is equal to L in the bottom, A times R. Right? So to have the length, you must have a ruler, correct?
Yes.
So the ruler has to be there. So it's not B. It's not C. Okay, how would you measure the R? By measuring the current and the voltage, right?
So ammeter.
So V is equal to IR. So you must have ammeter and voltmeter, right? And of course, who's going to give you the voltage? The battery. You must have wires. Choice D. Very easy. 43. Monochromatic light goes through a small slit of width W. Interference pattern forms on the screen at distance of D. Okay. So now look. Y is equal to M lambda L over D, correct?
Yeah.
So C is equal to lambda F. So lambda is equal C over F. So here you say M over D times L. Instead of lambda, put C over F. Now, what's W? The width of the slit, which is here. How far is the screen from the slit? D. This is D. Okay? So, this whole thing is equal to Y. Okay? And now we're looking for what? We're looking for the frequency.
Yes.
So now Y is equal to M capital D C over WF. So F is equal to W Y M D C. There, no one has M here, so leave the M. So DC over YW. Correct? Is that not there? Did I make a mistake? But where did that 2 come from? Actually, let's go back. The adjacent dark spot. Okay, that means that m is half. M is half. Okay, so now come back here and do it again. So now F is equal to YW in the bottom and half DC on top.
So it's A.
And it is, yeah, because the half means DC stays on top, 2YW. Good. Question 44. A beam of photons is incident on a solid metal sphere, initially neutral. That's wrong. Okay. Now, the photon energy, so the HF, is more than the work function. Metal sphere. So now, the electrons are going to leave it, correct?
Yeah.
And where do the electrons go? They go on the outside. They don't stay in the middle. Okay? But the electrons left. Right?
Yeah.
The electrons left. So what's left?
Protons.
Protons, or positive charge. Okay, which will go in the... Good. Okay. Quit. Now those questions don't come like this anymore, but you still have to know, you still have to know the information. The questions where they say select two answers, they don't come anymore like this.
Think better.
But still important. 131.
They're okay.
The piston is moved outward. That means that delta V is positive, work is negative.
Yeah.
Speed depends on temperature, correct?
Yes.
It's thermally insulated. That means that the Q is 0. So delta U is equal to work.
Yes.
So because work is negative, delta U is going to be negative. Temperature will decrease.
Yeah, so...
Speed will decrease. So it's not A.
It's not B. It says increase the force.
I mean, you're expanding it, right? So
It's not B.
you're going to have more volume, less pressure, less force. Correct? The pressure will decrease. And if the pressure decreases, you're going to have less collisions.
Easy.
Yeah. 132.
I mean, it's better to pick two answers.
No, if you pick two, if you must pick both correct.
No.
Yeah.
That's crazy.
I know. 132. Non-conducting plate with a negative net charge is held at rest. A conducting sphere with a net charge of 0 is moving at the speed of v away from the plate. So look, what's the charge on this sphere? Negative.
Negative.
Otherwise, how is it getting repelled, right?
Common sense.
So it's feeling a force.
Yes.
So is that force on 0?
No.
No. It's moving away. That means it's using up electrical potential energy of the system, right?
Yeah.
So it's not C. Whoa, what's left? Two choices.
So it's B. Oh, okay.
B and D. It's accelerating, right? I mean, it's increasing in speed.
Yes.
Actually, wait, there's a mistake. The sphere is not negatively charged. The sphere has a net charge of 0. So now, when you have a neutral sphere, it will feel attraction toward the negative plate. But now it's moving away, so it's moving against the attraction. If it's moving against the attraction, the potential energy of the system is going to increase. Which is why it will decrease in its speed, which is why momentum will decrease.
Okay.
So it's B and C. Get that right next time. 133. Conducting plate, non-conducting disk. Non-conducting disk has uniformly distributed net negative charge. conducting plate with net charge of 0 is held near the disk. We connect the plate to the ground, correct?
Yeah.
So all the negatives, okay, miss. The wires then, so look, when the plate is connected to the ground, right, the negatives will be repelled to the, what? To the ground,
Yeah.
correct? So now it's gonna be positive because the ground will take all the excess electrons. A conducting plate with a net charge of 0 is held near the disk. A wire is then used to connect the plate to the ground. The wire then is cut.
So it will be left off with positive charge.
From the plate to the ground. Yeah, that's correct. Okay. Do they attract each other now?
Yeah.
Because they're oppositely charged, right?
So it's B, A and B.
Yeah, and now they attract each other, so now they want to move toward each other. So now if you move them away from each other, that's moving against normality, which means you're going to have more PE, not less. So it's not D. So it's A and B.
Yeah. Very interesting.
Alright, 134. A circuit consists of a battery and identical resistors X, W, and Y.
Yeah.
A fourth resistor Z is added to the circuit. So the current in Y decreases. So the current in Y decreases, right? Let's see how much current right now. Let's just say this is, they're in parallel, right? So 1 over R plus 1 over R is 2 over R, and you flip, you get R over 2. You add it to this one, you get R. That's 3 over 2R, right?
Yeah.
This is EMF. EMF is equal to I times 3 over 2R. So now I is equal to 3R here, 2 EMF. The W will get the full I, correct?
Yeah.
But these ones will get only half. So you get 1/3
And 1/3.
and 1/3. Currently, right? Now you want to decrease the current in Y. Okay? Right now, if you were to add this new resistor Z in parallel with W, right? So that means here. Now what's going to happen? You're going to have parallel, and what's going to happen basically if you add more parallel?
Decrease.
If you have more parallel, you're going to increase the current in total.
Yeah.
Correct? Yeah, if you add more parallel, you're going to decrease the
okay.
resistance and therefore, so it's not going to be that one. If you put it in series with X, like you put it here, you're going to have also, so this guy will be 2R. This guy is R. So 1 over 2R plus 1 over R is 2R, 2. So R plus R is 2R. That means you brought the resistance up.
Yeah.
Which means you brought the current down.
So B is right.
So B is right?
What if I think it's B and D?
Wait, so B is right, correct?
Yeah. Because if you put it in parallel with Y, you will increase the current, right?
Wait, so the R goes up, the I goes down. And now the whole thing will get less current, right? So B is possible. And in series with the battery, Yeah, you're right, because you also will get more things in series. So it's B and D basically, right?
Yeah.
Where I take it back. Because if I put it in series with X, this guy will get 2/3. So no, it will get the same as before, so it's not B. D is okay. If I put it in parallel with Y, then what's gonna happen is I will have these guys. I'm gonna have R over 3 plus R. Okay, so I'm gonna have 4R over 3. Okay, now this guy, so the W gets EMF is equal to I times 4R over 3, so I is equal to 3 EMF over 4R. Okay, now each one's gonna get like 1/3 of that, right? So 1/4, yeah, which is less than 1/3. So C and D.